Okay, time to get started. Raquel's question.
Are we gonna have homework next week on Wednesday?
Homework next week, yes.
When are you gonna put it up?
I'll probably put it up Sunday. Is that a problem?
Well, I just want to do it as soon as possible. So midterms.
Okay. On the potential test questions, please make sure that you write your potential test question about something that we talked about in class. There were 3 or 4 of them from the last lecture that were not things we talked about in class. And they're supposed to be based on what we talked about in class, so everybody knows the answer because they heard us talking about it. So please try to make sure you get that covered. Okay, we're going to look at chapter 14 today. And chapter 14 starts off by saying chemistry is the central science. Now, we've already talked about physics, and we said physics was, and there was a word that the textbook used, the blank science. What did we use for physics? The fundamental one. And now when you say chemistry is the central science, that seems to be kind of a contradiction, because central and fundamental to me are pretty much the same. Well, what he means by this, and you can see a fine little graphic where you have chemistry relates to physics, and it relates to geology, and it relates to all the other sciences. So I only wrote 2 here, but that's what the author means when he says chemistry is the central science. It relates to everything else. It's not fundamental to the other things, but relates to them. In chemistry, we're looking at the submicroscopic world. We're looking at things that we can't see. Even with the microscope, we can't see it. Otherwise, we would call it the microscopic world. Submicroscopic, we're looking at things we can't see. And so we have to try to determine properties, and from those properties, determine what's going on. So let's get into this. So first, chemistry is the study of matter and the transformations it can undergo. Those transformations is what chemists are concerned about. How can A affect B and the changes that go on? And we use chemistry in lots of things. Now, I don't know about you guys, but my wife argues with me vociferously about the definition of chemicals. The definition that she says everybody knows chemicals means this, and I say, but that's not what it means. And of course, or certainly the American Chemical Society is pretty adamant that's not what it means. So what does chemical mean to you?
Like a mixture of different, not elements, but
Okay, mixture something.
I just think of bathroom cleaner.
Of what?
The bathroom cleaner.
Bathroom cleaner?
I confirmed.
Of what?
I confirmed.
You confirmed that's bathroom cleaner? That's what chemicals means?
Correct.
Any other answers? Well, here's the thing that gets chemists all worked up. Are chemicals dangerous?
no.
They can be. Some are. Some are not. Chemicals are, Brandon had the right answer there. Chemicals are just elements, maybe these 2 elements together, these 3, or so on. In fact, let me jump to vocabulary that's we've gone over that I have a clarification coming up. The last class period, a student asked about the difference between a compound and a molecule. And I'm going to add one more word, element. Because the differentiation between these words, between these words is useful just to, when the words come up, you know what they mean. So element we've talked about. What is an element? Okay, one type of atom. And we have a slide coming up on elemental forms. And so I'm just going to stop there with one type of atom. A compound is two or more different types of atoms.
So if it's like two of the same atom.
That is the key. If it's two of the same atom, it's still an element. But if it's two different types of atoms, like sodium and chloride, or sodium and chlorine, then that's a compound. So where does that leave molecule?
Isn't that like different compounds?
It's two or more. Actually, it doesn't even have to be two. It could be one, two, or more atoms bound together.
Like what?
Okay, like what? Right? Seeing the examples helps you to understand. So, helium comes by itself. What would we call that using the first two terms? An element. So this is an element, but it's also a molecule. It's a monatomic molecule. It's one atom in the molecule. Then we have something like, let's say O2. What is that?
Element.
Okay, it's an element. And now it's a diatomic molecule. What about CO? That is a compound and a molecule.
So everything's a molecule.
Pretty much, a molecule is a unit that is bound together of atoms. And that could be just one atom. It is not bound to anything in that case. It's by itself. So actually, I made one mistake in my answer. I think it was Candace that asked, and she's not here today. I said that the compound was more general, but it turns out the molecule is the one that's more general. Right? Because the molecule is any atom or atoms that are held together as one fundamental unit. Compound, you have to have two different types of animals. I should give up on speaking. I had this weird thing this morning, like I was teaching in German, auf Deutsch, or maybe switching into Japanese, Yeah, might as well be teaching Japanese when I use the wrong words. Anyone speak Japanese? Good, then I'll say like 5 words and I'll sound fluent. So here's a picture from your textbook of a kitchen scene. What chemicals do you see here? What are chemicals? Chemicals are all the things I just talked about. The compounds, the elements, the molecules, all those things would be chemicals. So what chemicals do you see here?
The tomatoes.
What? Okay. These here. Those are made of chemicals, right? Those are produced by the ground. The actual atoms weren't produced by the ground, but putting the atoms together the way they are was produced in the ground. So those are chemicals. Yes.
Wait, is like a single element a chemical? Or is it
A single element is also a chemical. Yeah. All of the things I talked about here, all of these are chemicals. Okay, so we had the vegetables and fruit, because of course everybody knows tomatoes are fruit. You know that thing between knowledge and wisdom. Knowledge is knowing that a tomato is a fruit. Wisdom is not putting the tomato in your fruit salad.
Yeah.
Yeah, you heard it. Okay. So what other chemicals do you see here? What other evidence of chemicals? Okay, over here. Okay, so the microwave, we have a lot of things that we could point out there. We have probably a glass surface on it, and the glass is going to be, of course, silicon and oxygen. The textbook actually points to the window here for glass, right? Because you have the glass there. And then you have the metal around it. The metal is another chemical that has been manufactured. And, well, by now you're probably getting the point. Everything you see in here is chemicals. Everything you eat is chemicals. And you know what? A lot of those chemicals are really good for you and you can't pronounce their names. Sometimes you'll see really unintelligent sites that say, if you can't pronounce the name, you shouldn't put it in your body. Which means most people shouldn't ever take any vitamins or anything besides water, because we can pronounce water. So here's the book pointing out different things. So we have things like the countertop here is a thermoset polymer. Polymers are chains of atoms. Our DNA is also a polymer. Prescription medicines inside the refrigerator, well, certainly you can't see those. Chlorofluorocarbon-free refrigerating fluids, you can't see those either, but the stuff that you use in the refrigerator pumps. Chemically disinfected drinking water, yes, because we do not want to have water that has, Giardia in it, right? And so we do things to filter and clean it. The transparent matrix of processed silicon dioxide. Yeah, that's actually, I guess it's pointing to the window in a cupboard, but that's glass. Silicon dioxide is that's what quartz is. And so if you take that silicon dioxide and you process it, you can make all kinds of different types of glasses. This one here, the caffeine solution. Yeah. Of course, water is a chemical, so is caffeine. The fertilizer grown vegetables, that was the first one pointed out. Natural gas laced with odoriferous sulfur compounds. You guys know the smell when you open up the gas jet and you have gas leaking? That's not the gas you want that you smell. The gas you want, the stuff you burn, is pretty much odorless. So they put in some sulfur compounds to give it a sharp smell so you know when the gas is leaking. It's not actually part of the gas that you want. It's an additive so you can smell it. Because most people think that's the smell of the gas. Because when you smell the gas, you smell that. Metal alloys, I talked about the metal when we were talking about the microwave front. Roasting carbohydrates, fats, proteins, and vitamins. That is an alternate pronunciation of vitamin. And yes, I do normally say vitamin. That's food, right? Carbohydrates, those are chemicals. Fats, chemicals. Proteins, chemicals. And vitamins, chemicals. Yes, coffee. So all of these things are chemicals. So when we're studying chemistry, we're studying all of these things. Of the things listed here, not all of these would you want to eat, right? I would not want to eat, for instance, the metal alloy. I wouldn't want to eat the thermoset polymer. Personally, I wouldn't want to eat most of the fertilized grown vegetables here. But not all chemicals are good. Not all are bad. Some are good, some are bad. So I said that it's a submicroscopic world. This slide here is just to get us in the mindset, this one and the one following, about exactly the size we're talking about. So 1 grain of sand, something that's about that size, contains 125 million trillion atoms. What is a million trillion? There is a name for a million trillion, right? After trillion comes quadrillion, and after quadrillion comes pentillion. So they could have just said 125 pentillion, but most people wouldn't be comfortable with that. And we're nowhere close to a Google, so can't go that way. Now, that's a really big, phenomenal number. Agree? And that's how many atoms just in a grain of sand. So how many grains of sand how big would that be? Well, if you had 250,000 sand dunes the size of this baby, that would be the number of grains of sand equal to the number of atoms in 1 grain of sand. That helps you get a better perspective of just how many atoms there are in things. Really, really tiny. So I don't know why, but the preset slides had like 5 different versions of that sand dune. So when we're studying chemistry, we're going to study 2 things: physical change and chemical change. A physical change is a change in the physical property, something like how hard it is or how dense it is or something like that. So let's take a very common chemical, water. We have water comes from the faucet. That water is in a liquid state. That's a physical state. And if I take that water and I throw it out on the sidewalk right about now, what's going to happen to that water?
It'll freeze.
It'll freeze. And it changes from being a liquid state to a solid state. So that's what we mean by talking about the physical change. But then we can do other things with water. I can take water and I can mix it with elemental sodium. If I say elemental sodium, what do I mean?
Sodium is.
NaCl.
No, elemental means it's just Na. So elemental sodium is a rock, but it's very strongly reactive with water. When you put it in water, it blows up. There's a chemical change where the sodium is reacting with the molecules of water, breaking the molecules apart and forming new chemicals with new chemical formulae, different groups of atoms. So that's a chemical change. So we're going to be looking at those two things. So substances are identified both by the kinds of atoms and also how those atoms are connected to one another. You can have two substances that have the same chemical formula that actually behave differently. So it's more than just the formula, but for now we're going to worry about formulas a lot. So we're going to spend, well, hopefully our last 5 to 10 minutes in class learning how to name chemicals. And of course, we're going to be very simple. You know, if you, like I know we have a number of students here from CVA, that number's at least 2. And I know Nathan had to go through a lot of learning how to name chemicals, a lot more than we're going to do in this class. Okay.
It's a cute slide.
Yes, physical properties. What we have here are diamonds. Diamonds are, according to the big marketing campaigns to try to fleece money from you, a girl's best friend. And then we have gold, which I assume must be a boy's best friend, just by contrast. And we have water.
Everyone's best friend.
Yeah. If we look at these, we have, well, do you know what a crystal is? A crystal is something where the atoms are in a very intricate pattern that repeats over and over and over. So if you look at this, do you see any crystal evidence? Yes, Brittany does. What do you see, Brittany? Okay, diamonds. Diamonds are crystals. Diamonds are very complicated crystals. They're actually elemental, though. It's only one atom, carbon. But that carbon's in a very complex arrangement. You can take the carbon and put it in different arrangements and have elemental carbon that's completely different. An old school pencil used graphite, and that graphite was also elemental carbon, but it's in a different arrangement. So that's the same chemical, well, the same element, but you have different arrangement of the atoms to give different property. Gold is also a crystal. The atoms in the gold are very reproducible positions. So both of these are crystals. A lot of people think only the gemstone's crystal. And they forget that, yes, this here is, well, it's a bunch of crystals. It's a lot of crystals that are put together, but it's crystalline in form. Liquids are not crystals, except for we have a special category called the liquid crystal. You know, you have an LCD liquid crystal display. Those are liquids that have a reproducible positioning, which is an oddity. Now, if we look at transparency, this crystal, the diamond crystal, is transparent, and so is the water. But the gold, of course, is not transparent. So transparency doesn't belong to one state. It can be in a liquid or a solid, or, of course, a gas, because there's gas between you and me, and we can see through it. These are all at the same temperature. So we can have different phases at the same temperature. The air in here is roughly the same temperature. And then we have something that distinguishes a lot of things. The densities. That gold is extremely dense. What does that mean about the weight of one of these gold bars?
It's heavy.
It's heavy compared to what you would expect. If it was made out of lead, it'd be about half as heavy. And if it's made out of iron, it'd be like half of that. I didn't look up the number for iron. But, gold is really, really dense. Whereas water, comparatively, is very low density. And air is, 1/800th the density of water, roughly. Chemical changes. There have been some chemical changes to the metal of this car. It's rusted. That's a natural chemical process. You have the car is exposed to oxygen, and the iron in the metal has a chemical reaction with oxygen to produce a new compound of iron combined with oxygen. And so if you are a chemist, you say it oxidized because the oxygen formed bonds with the iron. If you're a normal person, you say it rusted. They're the same thing. And something that's surprising probably to most people, you know that Mars is the red planet, right? Why is it red? Because it has a lot of iron that's rusted. It has an atmosphere that's very, very thin, about 1/100th as thick as ours. But there's still enough oxygen to interact with the iron in the soil to rust it. And we also have the same thing. We have a lot of soil on Earth that has a reddish color because it has iron oxide. Here are some examples of physical change. You have water in the solid form, the liquid form, going from liquid to vapor. Those are not changing the chemical structure. In all cases, this is, if you zoom in, you can see H2O. Oh, actually, this here was mercury that was being vaporized. I don't know why they're focusing on the mercury, because this here is H2O as well. That's what I was focusing on, the steam. You have a physical change. They're showing the mercury of it expanding when you heat it up. So the mercury comes up to here in this one and comes up to here in this one. So the mercury expanded. That's also a physical change. So that's not a chemical change. It's a physical change. Here's examples of physical changes. I like this one here. I should have done this for class because I've never done it before. Baking soda reacts with vinegar to form carbon dioxide and water, absorbing heat. What does that mean is happening if it absorbs heat?
It's getting hotter.
Well, it's going to have heat that flows into it, so the stuff around it is going to get colder. Now, when you say getting hotter, that heat that's flowing in is actually not going into raising the temperature, but going into making the reaction work. But from the outside, if you touch it, it's going to feel cold because you removed heat from the thing that's containing it. So you would have the beaker there would get cold as the reaction goes. And you have the bubbling that's producing carbon dioxide. And then we all collectively go, oh, carbon dioxide is bad, right? It's a greenhouse gas. Why would I do this demonstration to produce a greenhouse gas? Well, the answer is it's a really small amount of this greenhouse gas. If you burn gasoline in your automobile or burn wood in a campfire, you're doing a lot worse things. Copper has oxidized, turned to rust. You also, here's showing the combustion forming carbon dioxide from oxygen and the gas. Okay, let's just get to the fun of things. Here is a chemical reaction shown as a schematic relationship. So here we have methane. Methane is CH4. The way to read that, remember our elements, all of the atoms, their abbreviations start with a capital letter. If they have a second letter, then it's going to be lowercase. So when you look at this, you know C must be the entire element because the next letter is capitalized. So that C is carbon, and then the H is hydrogen. The subscript of 4 means there are 4 of them present. So CH4 is, if you want to use the naming conventions we're going to use in a few minutes, it would be carbon tetrahydride. But nobody ever says carbon tetrahydride because it has a common name. And the common name is methane. Now, I am not going to be holding you to memorizing many common names. But it's important to understand that there are common names and there are IUPAC names, the chemical names that follow a strict naming structure. And we're going to learn a little bit on how to make those strict structure names. The common names don't have a strict structure, so you can't learn, oh, we use this rule for naming that. So we have methane down here and oxygen. Oxygen is O2. You bring them together. What normally happens if you have methane and oxygen? Now, the gas that's coming out of there is probably propane rather than methane, but it's going to be the same idea. If I open the gas jet, and if I had the switch turned on, so gas flew out, what would happen?
Looks like we create carbon dioxide. Is that right?
You don't. That's why I asked the question. You don't. If you just turn on the gas and you don't put a flame in, nothing happens except you start filling the room up with gas. You have to add something that's not shown in this picture. You have to add something that we call a catalyst, something that's going to make the reaction occur. And in this case, you have to add heat. So you put something in there that's going to heat it up. What do we usually use? A match, because it only takes a spark to get a fire going. So you add heat, put the plus out here so it doesn't look like it's a T. And that heat causes the two to react. And that reaction, you see we had dissociation of the oxygen, dissociation of the methane. The process is more complicated than they show here. It's not just it all separates and then comes back together. Brittany.
Okay, so when you add heat, doesn't have to be like strictly just any heat. Like if you were just like
The answer is yes. It just has to be any heat, but it has to be enough of it. And so if you get it hot enough, it will burn.
if I just blew a heater right over it.
Yeah, if you have like a wire that's really hot, that will also make it burn. It doesn't have to be on fire. It's not that fire begets fire. It's the heat. Okay, but then once you've done this, it forms bonds to make lower energy situations. Remember I said energy is really important because it's what drives everything. When I drop this ball, it goes down because it's going to a lower potential energy. These reform to make lower potential energy molecules. So here we have carbon dioxide, that's CO2, and water, that's H2O. And those are bound more tightly. They're lower potential energy, and it releases the difference by releasing heat. So you had to put some heat in to get it started, but then it releases heat. And of course, if it's going to keep going, it has to release more heat than you put in. And so that's what's going on when we burn gas. We're putting in some heat. It makes it then undergo this reaction, which releases even more heat than we put in. So you don't have to keep putting the match there. Now, another thing that's important, are we creating or destroying atoms as we do this? We can't create or destroy it short of a particle accelerator and radioactivity. We can't create or destroy atoms. So the atoms are staying the same. So if we look here, we started with, how many oxygens did we start with in this picture? Two. So we had 2 O2 plus how many methanes? 1. So CH4 produces with heat And on the right-hand side, we have how many waters?
2.
2 H2O plus how many carbon dioxides?
1.
1. If we didn't create or destroy any atoms, we should have the same number of carbons on each side of our equation, same number of oxygens on each side, same number of hydrogens. So if we count these up, on this side I had 2 O2s. How many total oxygen atoms is that? Okay, so I had 4 oxygens plus how many carbons do I have? Plus, okay, that 4 oxygens looks like 40. 4 times oxygen plus 1 times carbon plus, and how many hydrogens?
4.
And then let's compare to this side. If they're not the same number for each one, there's a mistake. So on this side, how many oxygens do I have? I have in the water, how many total oxygens do I have in 2 water molecules?
4 total to the whole equation.
Okay, there's 4 total, but 2 in the water. So I have 2 oxygen here plus how many hydrogens here?
4.
Plus 4 hydrogen plus how many carbons? And then there's another 2 oxygens. So I combine those and we get what Casey had said, a total of 4 oxygens. So we have 4 oxygens, 4 hydrogens, and 1 carbon, the same as we started with. It's a balanced equation. And one of the things that, once again, Nathan is having fun with in his chemistry class is going through and balancing equations. You have this much of this and this much of this. What do you get for the products? And you just have to make sure you have it balanced. You have the right number of every atom. Okay. Both physical and chemical, this is obvious. Both physical and chemical changes can make it look different. Right? You change from water to ice, it looks different. You change from iron to rust, it looks different. So that's all this is saying. We can skip right by that and go to our first question. Melting a piece of solid gold would be what? Would it be a physical change, a chemical change, both, or neither?
Is the gold like in water?
No, just a block of gold becomes gold in a vat. A block of gold that I don't own. Brandon and Mickey.
It's like not long.
There are only 2 people who haven't answered a question yet, Hannah or Casey. So it's going to be one of those who's going to explain this to us.
Oh, great.
As soon as Brandon gets logged in. You can do it. There's only 2 questions, so you don't get credit if you don't get in. And I want him to get his credit.
I'm gonna skip. I don't know my password.
Okay. Okay, we had 11, 2, 3, and 0. So, Casey,
Oh,
give us your answer and your reasoning.
okay. Well, I mean, obviously, if you melt a piece of solid gold, is no longer a solid.
Okay.
So it has gone through a physical change.
Okay, so we have a
So-
physical.
At least A, for sure, is involved. And then I was thinking, this could probably not, it's probably completely wrong, but whatever. I was thinking that once you melt like, isn't the gold gonna have some sort of interaction with like the air molecules because it's a different like form, like some sort of chemical thing going on? But
Gold is actually, it tarnishes, right?
yes.
And so if it does tarnish, that's a chemical reaction. Tarnishing is also oxidation.
Okay.
So it can do that, but actually when you heat it up, it actually purifies it and gets rid of the tarnish. So it actually should be just the physical change, but your reasoning is good,
Okay.
right? That's always something that could occur when you do it.
I knew it was A, and I was like, it's possibly B. Like, there's a 10% chance it's B. I'm just gonna put C. You know, I was wrong.
Go with the 10%. Don't go to Vegas with that idea. 90% chance of this. I'm going for the 10. Okay. So this is where the definitions for atom element come in, and we're going to go through. So here's some examples of, it says compound. Yeah, that ain't right, is it? What are each one of these? They're elements. I didn't even notice that when I was going through and editing. I didn't see that. I did try to center these, which didn't work.
Why would they put compound there?
Because for a compound, you need two different types of atoms. But these they're all the same type. Right? This is all oxygen. Notice O2, we have a common name for it of oxygen. O3, we have a common name for it of ozone. They're both elemental in terms of it's just oxygen. But they have different ways of arranging, and they have different chemical behaviors, so different names. Sulfur, S8. Yeah, it's a unique one. I didn't know that you could make S8. And gold, just AU for Orium or something like that. I would say Ericium, but probably wrong. Why do I say Ericium? Because when I was a child, I read all the Bond move books, and there was Auric Goldfinger, and I had to look up Auric, and it meant gold, and I thought, ha, 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 he's so funny. All right. Now the definition of compound. A compound is a substance consisting of different elements, which is why that was not a compound. And so all compounds are molecules, but not all molecules are compounds. Because the molecules, for instance, that we saw here, were not compounds. So just some examples of different ones. Sodium chloride, this is showing sodium chloride with repeatable positions. What do we call it when we have repeatable positions? Crystals. So this is a crystal of sodium chloride. It's made of sodium atoms and chlorine atoms. But when we put them together, we call it sodium chloride. And that's part of our naming conventions we'll get to, I believe, in a minute. Then we have here ammonia. The ammonia is NH3, 1 nitrogen, 3 hydrogens. Again, that's a common name. If you want, well, we'll get to what it would be for its IUPAC name. So, yeah, I can skip through that. Let's get to the naming. So here's some compounds, really compounds now. Sodium chloride, NaCl, ammonia that we just talked about, and water. These are common names. And people would call you goofy if you went around calling them like nitrogen trihydride, right? That's what ammonium would be, or ammonia would be, excuse me. Ammonium is, I think, dihydride. But that's what we call them. So, naming conventions. Rule number one. Rule number one is start with the element that's the first one in the formula. So, in this one, that would be Na, natrium. What's natrium's name in English? Sodium, yeah. You can always look at the periodic table. You're not required to have these memorized. So start with the element farthest to the left, And then for the element to the right, add the suffix "ide." Now, Cl is chlorine. I said it says add the suffix "ide." You have to replace the "ene" with "ide." So you look at the periodic table. Here's sodium. Here's chlorine. And you say, okay, sodium. And first I'm writing chlorine, and then I'm changing that "ene." Whoops, that was supposed to be a different color. Changing that "ene" to "ide" to make the name of the chemical. So let's go with some, with different possible combinations of elements, use prefixes to tell you how many. So what are the prefixes? Mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, so on. So how would you name this element? Or not this element, this molecule?
Carbon monoxide.
Okay. Carbon, because it starts with carbon, has 1 oxygen, but you could have 2. So you put monoxide. And of course, you don't put monoxide. Excuse me? Yeah. I thought I heard tries. Yes. This one here is carbon di because of 2 oxide. So, yes, these here. I forgot I was going to put them without the names. Don't look, everybody. Brittany has a question.
I missed something in the slide before.
What'd you miss?
So like, how come we didn't call this sodium monochloride?
Okay, why did we not call it sodium monochloride? Right, because that's accurate. There's only 1 chloride, right? Or only 1 chlorine atom. Because we don't have an option of having 2 Cls. So it's only if you could have more than 1. And then the question comes, how do you know? Right? A priori, you don't know. It's not until you're into chemistry that you know. But that's the reason, nonetheless. Is that what you're going to ask Tiffany? Is how do we know?
Yeah.
So if like we were like we put that as an answer for something and it's like, well, there's no way you can have 2 of them. But we're still technically correct.
You have a good point. I'll try to make sure we don't get into that situation. You know, I can use wording such that we can avoid it, and I will try to do that. Okay, so let's look at the 2 that are on the next one. This top one. What's the common name? Water. But if we're going to use the IUPAC name,
I'm gonna just start calling it
dihydrogen, how many oxides? Monoxide. I was speaking with a student a couple days ago, and the student was saying dihydrogen oxide. And really, you need to say monoxide because you have the one below. Whoops. The one below looked identical, but now it's not. What's the name for this? What's the common name for it? Hydrogen peroxide.
Why is that?
Okay, the per is telling us about the oxidation state, which is beyond what we're going to learn. So this is using a little more sophisticated terminology to get the hydrogen peroxide. There's one that's not shown here. I'm not going to write it down. OH. OH is not neutral. OH has a net negative charge. And so that's actually becomes really important when you talk about acids and bases. Water breaks up into an H and an OH. And if you have more H's, then it's, I believe, more acidic. I have to go back and check to make sure. Proton donor versus proton acceptor is the difference between acid and base. But we won't go into that right now. So those are the names for those 2. Now, a joke that you can understand. 2 chemists go into a bar, and the first chemist said, "I would like a cup of H2O." Gets his cup and drinks it. And the other chemist says, I would like a cup of H2O2. And he gets his cup and he drinks it and he dies. Why? Because H2O is water and H2O2 is dihydrogen dioxide or hydrogen peroxide. And hydrogen peroxide isn't very good for you. In fact, how many people put hydrogen peroxide on your cuts? You shouldn't. You shouldn't, because it will actually cause the blood cells to burst and kill tissues and stuff. So you can use it to clean around the cuts, but you shouldn't put it in the cuts. Well, it's bad if you have a cut somewhere, and I don't know. Yeah.
So, okay, I've gargled with it before. Is that a thing?
Yeah. As long as you don't have cuts, it's great because it's going to kill all kinds of biological things, like the bacteria that give you bad breath. Now, one thing to keep in mind, like I love antibacterial hand soaps because I'm killing all that crap on my skin. We need bacteria on our skin. It's just, the right ones. We don't want things like E. coli on our skin, but we need bacteria. And other things to really gross you out, they've done studies where they study the flora, the bacteria on a person's skin before a basketball game and after a basketball game. And it completely changes because you know what they did? They were contacting other players while they were playing basketball and they exchanged bacteria. And so their own personal flora changes because of that contact, okay? Good to know, right? Come on, work with me. Okay, so rule number 2 was putting them together and adding "ide" to the second one. And there's a reason why it's adding "ide" to the second one. The rule number 2 was using prefixes, and then rule number 3, common names are sometimes used for convenience. So we never say, dihydrogen monoxide unless we're trying to scare people about this scary chemical. Everyone who has ever died has ingested dihydrogen monoxide. And yet we put it in our food. How crazy are we? You guys have seen those, right? Lampooning the people who don't understand chemistry. Yeah. They talk about, something you put in bread that helps it to rise, and it's used as fire retardant and in yoga mats. And yet we put it in our food. Water is also really good for fire retardant, but we put that in our food too. Okay, enough on that. What's the name of this chemical right here? And we all know who's going to tell us the answer, don't we, Hannah? Hey, Brandon got in now.
Yeah.
Thank God I didn't try to use it on my phone because my phone is dead at the time.
Okay. Oh, but
Actual question, how the heck are you supposed to charge these things? You get new batteries?
I think you get new batteries.
Or there's chargers.
Are they chargeable?
Mine is chargeable.
Interesting.
Okay, I didn't know that. I was not aware of that. Okay, 0, 0.
I did.
Yeah, I got your answer. I didn't stop until I got your answer. 314. So, Hannah Moralia. What is your answer and why?
I said B because we changed the suffix to "ide" like we're supposed to, and then it added the prefix. I didn't know that was the prefix for 4, but it was the only prefix.
And it is the prefix for 4. And so you're absolutely right. Carbon tetrabromide. I liked this question and left it in because I wanted to see if anyone would say Sieber 4, which would just be funny. No, nobody did. I would not have made fun if somebody had said it because, of course, that's not a good way to treat your
Did
students.
you use this last year too?
This is the first time I ever taught this class.
Oh.
So no.
Oh. Yeah.
Okay, that's the end. I finished every single slide in our allotted time.
Wow.
Have a happy weekend. Happy Sabbath.
So,